Good morning, good afternoon, or good evening, depending upon where you are in the world, and welcome to today's webinar. Troubleshooting Switched Mode Power Supplies, brought to you by Rohde Schwarz, Tech Online, and broadcast by UBM. I'm Chris Keach, and I'll be your moderator today. We have just a few brief announcements before we begin. First, you can participate in the Q&A session by asking questions at any time during this webinar. Just type your question into the Q&A text area located to the right of the presentation window, and then click the Submit button. At this time, we recommend you disable your pop-up blockers. The slides will advance automatically throughout the event. You may also download a copy of the slides by clicking on the Additional Resources button located below the presentation window. And if you're experiencing any technical problems, please visit our webinar help guide by clicking on the help link below the presentation window. In addition, you can contact our technical support helpline, which is also located in the webinar help guide. And now on to the presentation. Troubleshooting Switched Mode Power Supplies. Discussing today's topic is Mike Schnecker, Business Development Manager, Rohde Schwarz. Mike has 22 years of experience in the test and measurement industry in applications, sales, and product development roles, and has specialized in signal integrity applications, including jitter, using oscilloscopes and other instruments. Mike, I'll now hand it over to you to begin today's presentation. Mike?
Thank you, Chris, for that introduction, and thank you all for joining us this afternoon. We're going to spend the next, I'd say, 45 minutes discussing switch mode power supply measurements and troubleshooting those devices. Here's a quick overview of what we plan to talk about. It's a little agenda here, and some might want to push that slide for me because it ain't working now. Thank you very much. So a quick overview of the agenda today. We're going to talk a little bit about background on switch mode power supplies. This will be a very quick introduction just to get us all sort of on the same page. Then I want to talk about a measurement setup that would be used to test this sort of hardware. And I want to spend a little more time on oscilloscope measurements, really getting the most accuracy out of these measurements, and some of the considerations such as how to adjust the oscilloscope display, what sort of probing and bandwidth requirements are out there and would be required for measuring these types of things. And I'd like to finish off by going through a measurement example. So we're going to step through some measurements on a switch mode power supply and show sort of the critical measurements that could be made and what you can learn from them. Let me try to advance this myself. So for some reason, I'll take an advance, please. There you go. Thank you. So give it a second to show up in your window here. The diagram.
The audience is seeing slide 3.
Okay, because I'm not seeing it. Okay, thank you. I assume it's with the audience. Sorry about that. So this is a very quick schematic of a switch mode power supply. What we're seeing here is a basic DC to DC converter. Essentially the kind of thing you'd find in a lot of different applications and computers and other hardware. We're showing this, obviously, there's a couple of switches on here. There's 2 switches that are normally implemented using transistors, such as MOSFETs and FETs, that switch the source, the V sub G, the source on the left, alternately towards the inductor on that diagram, or switching from the inductor to ground. And there's basically 2 phases to the operation of this. The key measurement points that we like to look at are the input voltage and current going into that structure, as well as the output voltage and current, critically, because that's what we're driving. What's shown as a resistor on the right-hand side is actually whatever the power supply would be driving. So in a lot of cases, that's more than just a resistive load. It could actually be a fairly complex load. And there's another key point that you'd like to measure, and that is the switch node, which is right between those 2 switches. Next slide, please. So here we have a picture of what the waveform would look like at the output of the power supply. So this is at the load, and again, in the ideal case, you would have a voltage that looks like V sub G for a period of time, which we'll call capital D times T sub S, which is the switching frequency. And then it will go down to 0 for a period of time that is 1 minus D times T sub S. the variable D being the duty cycle. And the idea behind the whole regulation process is that the average waveform voltage would be equal to the average of this waveform, and we can adjust the voltage output by simply adjusting the duty cycle dynamically. And so this is the job of the feedback control circuit that regulates the voltage. Thank you. And this is a picture of measurement on a real power supply. So there's actually two phases we're measuring here. So the yellow highlighted circuit shows what the configuration looks like when the switch is in the position towards the source. So now we're charging the inductor. And if you look at the waveform on the right-hand side, there are three waveforms superimposed. One is the switch node voltage, which indicates the voltage at that node connected to the inductor. And at that point, the voltage is equal to whatever the source voltage would be. In this case, it's, I think, about 5 volts. And during that interval, the inductor current is increasing, gets to a maximum value, and then we switch the switch away from the source and towards ground, which is shown outlined in blue. The circuit looks like that now. And there the inductor is discharging back through the load and the capacitor. And so you see this inductor current that is alternately increasing and decreasing throughout the switch cycles. And you can see the voltage at that node, which goes near 0. Now the inductor current is actually linear. So this is a diagram showing what the inductor current would look like ideally. And in this case, we're assuming an ideal inductor. So in an ideal inductor, the derivative of the inductor current is equal to the voltage across the inductor. So if you have a constant voltage across that inductor and the inductor is actually operating as a ideal or at least nearly ideal inductor, you'd have this linear variation in the current. And we're going to use that kind of later on as we diagnose power supplies. So one of the key elements of the design is that that current should be linear if the power supply is operating properly. So shoot off to the next slide, please. So the measurement setup that we would use for testing a typical switch mode power supply might include some or all of the equipment shown here. One of the key measurement tools, of course, is the oscilloscope, which would measure all the voltages at the various test points. And I guess the biggest question to answer here in the purchasing of an oscilloscope for this is what kind of bandwidth you'd need. Turns out that you need a fair amount of bandwidth, and we'll get into that a little bit as we discuss this. 500 megahertz or more is probably good, and this is because the switch node voltages tend to switch at very fast rates. So you're covering a lot of voltage in a very short period of time, very fast rise times and slew rates. In order to probe the signals throughout the power supply, a number of different probes are often used. The simplest is called passive voltage probes. These are just simply a resistive divider attached to the front end of the scope with a proper connecting point so that you can hook onto the circuit. Those can be used in cases where there is a defined ground, where you have a ground that is common to both the scope and the device under test. In some cases, you might have floating voltages where there's a common mode voltage. In those cases, it's often required to use a differential active probe, so there's maybe a use for those in some cases. And also, in a lot of cases, a single-ended active probe as well. They offer two advantages. For the differential probe, one is that you don't have to worry about the common mode voltage, which would be rejected. The other part is that in a lot of cases, the bandwidth of the signals that you're measuring are high enough to require an active probe, which provides lower loading and higher bandwidth. If you're going to measure current, there are a number of different current probes available. I'm showing here a picture of a typical clamp-on current probe. These would be used to measure the input and output current and also the inductor current, depending upon the design. If you're using different types of probes, a De-skew fixture is often helpful. The De-skew fixture allows you to assure that the measurements are lined up in time. This is helpful because the delay through different types of probes would be different, so that signals probed, for example, by the current probe and by the voltage probe might arrive at the oscilloscope at different times. And timing is very important when you're trying to measure things, for example, like switching loss. In some cases, the switch mode power supply would need to be driven by a source that provides some kind of a known voltage and current. And so a programmable power supply is often useful, at least when initially starting up these switch mode power supplies. Helpful to have variable voltage and current. The current variation allows one to limit the current, especially when you're bringing up the power supply so that, for example, you don't blow it up, something bad like that. Also, remote sensing is helpful so that you can guarantee a fixed voltage going into the device under test so that you can actually measure very accurately the regulation of the power supply. Off to the next slide, please. All right. When measuring switch mode power supplies, accuracy is kind of important and very difficult sometimes because of the large dynamic range of the signal that you're viewing. So that, for example, the switching voltage itself at the switch node tends to have a very broad range of values, from maybe tens of volts to even hundreds of volts, and in some cases thousands of volts in the on state to maybe a few volts or a few millivolts in the off state. So this is a pretty dynamic waveform and requires a fair amount of resolution to measure. And if you look at the typical oscilloscope A to D converters, they provide somewhere in the range of 6 to 8 what we call effective bits. And not getting into a discussion of that, but effective bits really represents the signal-to-noise ratio of the oscilloscope. And this is, if you're used to thinking in terms of signal-to-noise ratio, is about 50 dB or so of signal-to-noise. So this is equivalent to about 20 millivolts out of a 5-volt signal in the basic mode. So you need some tools to maximize the signal-to-noise, and there's a lot of features within oscilloscopes that allow you to do this. The first and most common way of improving the resolution is by simply doing waveform averaging. Waveform averaging will reduce the noise by simply smoothing the variation of that noise out over multiple acquisitions. Another technique that's available in almost every scope is something called high resolution mode. Also there's other modes, names for that mode, like maybe ERES. Different manufacturers refer to it by different names. But they all kind of work the same, basically trades off signal sampling rate for bandwidth, and it also improves the signal-to-noise ratio. Another, maybe not directly related aspect of this is using multiple grids, which we'll talk about. It's always good to have waveforms not on the same grid, but on separate grids on the oscilloscope screen, and we'll show you what this means in a moment. Another issue that's important to keep in mind is the probing. Probing can cause a lot of errors, and it's important to have both the correct probes with the right accessories and the proper bandwidth. As I mentioned, the switch mode power supplies can have very high bandwidths and very high slew rates, and often have high frequency content well beyond the switching frequency. So probing is very critical for capturing all of this information and getting the most information about what the signal behavior is like in your power supply. The oscilloscope bandwidth and sampling rate are also critical. So again, you need enough bandwidth to capture all these high frequency signals, but you also need enough sample rate to capture accurately the bandwidth that you're trying to view. And we'll talk about this in a moment as well. Next slide, please. So waveform averaging works very simply. On each acquisition of the oscilloscope, the waveform is averaged with the previous waveform. And this is a very simple effect of averaging out the noise. It effectively reduces noise from thermal sources that are random, but not all noise sources. So if there is a noise source that is actually deterministic or periodic, that will not be averaged out. And if you look at an oscilloscope trace, what looks like noise on the trace can come from a number of sources, including non-random sources, and those will not average out. One of the side effects of averaging is because of the action of the feedback loop in the power supply, the duty cycle of the pulsing changes. And what we're looking at here is actually the waveform from a switch node on a switch mode power supply. And that pulse width will change over time, and to the degree that it does change, there will be some smearing of the edges simply because the waveform is not the same each time it's averaged. And so one has to be careful about how many waveforms you average relative to how quickly the feedback circuit is changing that pulse width. The smearing can actually can also result in reduced rise time measurements because of that averaging of the waveforms that are varying in time. Let's go to the next slide. The other technique that is used commonly is called high resolution mode, or ERES mode. This is a variation on averaging. It really is, in fact, just averaging, but rather than averaging from sweep to sweep on the oscilloscope, we're going to average consecutive values out of the A to D converter on the oscilloscope. So let's say, for example, I have a 10 gigasample per second oscilloscope, and if I lower the sample rate to 1 gigasample per second and simply average 10 consecutive samples out of the A to D converter to get each sample displayed on the screen, I essentially get an averaging rate of 10 to 1. So I actually get gain from that averaging. The side effect of that is it does reduce the bandwidth because now my sample rate is slower than it was, and so my bandwidth is now limited a little bit more than it was at the higher frequency. But the benefit of this is it preserves the real-time update rate of the instrument. So therefore, you don't have to worry about the smearing of the edges and the distortion because we're not averaging over multiple acquisitions. So this is often very effective when looking at signals that have a lot of variation vertically on them in order to preserve the details of that. It's important to combine enhanced resolution mode with some sort of a low-pass filtering. The reason for this is that you might end up with what's called signal aliasing that occurs when you undersample. And so it's a good idea to apply filtering. Sometimes this is automatic in the oscilloscope. Next slide, please. Viewing multiple waveforms is a common thing within switch mode power supplies, and this is not a trivial thing. So typically when you have an oscilloscope with a single grid, you will show the two waveforms under test in this way. And basically shift one up on the screen and reduce its size, and then shift the other one lower on the screen and reduce its size. What we're viewing here is actually a switch node voltage and the output voltage ripple from a power supply. The problem with this method is that the digitizer bits of the ADC are distributed across the grid that you're viewing. So in this case, I have an 8-bit ADC. The 8 bits divides that vertical range into 256 levels. And so by reducing the waveforms in half, I'm basically throwing away resolution when I do that. A preferred method for viewing two waveforms is to use separate grids, which we show on the next slide. So let's move to the next slide. And on this slide, we show the same two waveforms, but now each one is in its own grid. And we can see on the lower grid, the ripple waveform, and the upper grid is the switch node waveform, but each grid now has its own 256 levels of digitizing. And so we actually retain the full resolution on both grids rather than having thrown away resolution by putting them both on the same grid. The next slide, I think I'm advancing myself now. So this basically reduces the resolution by half. This picture here shows a comparison between the waveform that was shown on the half scale, that is on half the grid, which is shown in kind of a pinkish purple color there, and the full scale waveform, which is a dark black waveform. And you can see the difference in the resolution pretty clearly is about twice the resolution on the full scale waveform. And this is because, again, we're throwing away resolution by reducing the signals on the screen visually. What I did here, by the way, to show these waveforms more clearly is I interpolated them using a sample and hold interpolation, which accentuates the bits. Normally on an oscilloscope screen, you would see them interpolated with a line, and you wouldn't see these jagged edges. I just set the mode that way to observe that. Another issue that's important is the bandwidth and also the probing geometry that you use to test the signals. We're showing here two pictures on the left and on the right. Both are taken of the output ripple voltage on a switch mode power supply. The left image was done with a normal passive probe with a relatively long ground lead. So if you've seen most oscilloscope passive probes, they have this kind of long hooked tip on them, and then they have a long ground lead with an alligator clip on them. That kind of geometry is very convenient for connecting to circuits, but it also has a significant amount of capacitance and tip inductance, which causes a resonance at the probe tip, which can cause ringing and overshoot. And it can affect measurements pretty dramatically. On the left-hand side, we're measuring the ripple voltage peak to peak on those two little spikes there. And while it's not quite visible in your slide, it's reading about 380 millivolts peak to peak voltage for that ripple. On the right-hand side, we're using the same probe, but now we're using a very short ground lead. So we took off that long alligator clip lead and we took off the hook from the tip, and we used a very short ground lead. And just by doing that, shortening that ground lead, we've reduced that measurement from 360 millivolts to 180 millivolts peak to peak. And the only difference there was that the resonance was moved out and beyond the signal that we're measuring so that you don't have that error. And again, it's all about getting the leads as short as possible. Now, the one limitation of passive probes, however, is bandwidth. So in a lot of cases, you only get about 500 megahertz or maybe less of bandwidth out of a passive probe. So in order to see a better picture, it's sometimes helpful to have an active probe. And this image that I'm showing here is the same ripple voltage, but now measured with an active probe. This probe is designed to have a much broader bandwidth. In fact, in this case, it's a 1 gigahertz bandwidth probe, and also has very low tip capacitance and inductance, and again, very short leads leading to the test circuit. Here we're measuring a peak-to-peak voltage of about 80 millivolts, so we've actually reduced the overshoot even more. And the reason for this, there could be multiple reasons. One is that a lot of times when you reach the limit of bandwidth of a probe, it actually starts to ring at a higher frequency and still has residual overshoot. But in the case of an active probe, you might actually see a bigger value depending upon what's going on in your circuit, or if you have any high-frequency interference that's outside the bandwidth of the probe. So it's good to have an active probe available just to get an idea of what's going on at all frequencies. And in this case, we actually got a much more accurate measurement of the peak-to-peak jitter, or I'm sorry, ripple. Another consideration that's not so obvious is the idea behind vertical resolution and the slew rate. There's two pictures shown here. The upper image is a rising edge of a switching pulse that's sampled at 5 gigasamples per second. So the sample points are 200 picoseconds apart from each other. And again, what I did here is I set the interpolation mode to sample and hold. So rather than the normal interpolated waveform that you see on the screen of an oscilloscope, I purposely set it up so you can clearly see the steps in the A to D converter. And the reason I did that is it makes it easier to see the resolution. If you can imagine, the oscilloscope grid is divided into horizontal and vertical divisions. The vertical divisions are determined by the A to D converter bits, and the horizontal range is determined by the sampling interval. So when you're trading off, for example, and looking at a fast edge like this, the signal changes amplitude very fast. For example, this signal here changes at a rate of 4.4 volts per nanosecond. That means that between sample intervals at 5 gigasamples per second, the signal is actually moving over 880 millivolts of amplitude. This is a lot bigger than a bit. So essentially having more bits in your A to D converter doesn't help you on these edges, because if you're not sampling fast enough, you still can't see the resolution you want to see. In the lower trace, we're showing the same signal at 4.4 volts per nanosecond, but now we're sampling it at 1 gigasample per second. The steps are much bigger in this case because it's actually about 4.4 volts per step. So it's much, much bigger than the resolution of the A to D converter. So trading off sample rate for resolution in bits one has to be careful, because it depends on what part of the waveform you're measuring. So the rule of thumb is if you're measuring the transition, the rising edges and overshoots, then you want to have high sample rate, and bit resolution is probably less important. So when you're measuring things like rise time and overshoot, averaging is not probably something you need to do. But when you're measuring the flat part of the waveform when the switch is in the on state or the off state, then averaging is helpful because the signal is fairly flat versus time, but the resolution helps you see more detail in that flat waveform. So again, you need to have both sample rate and resolution. You can't really trade off one for the other, especially on these fast edges. So this is just kind of a summary for slew rate and vertical resolution. Again, make sure you use the highest bandwidth probe that you can, again with the shortest possible lead lengths, and if possible, an active probe is a really helpful way of getting accurate measurements on especially things like output ripple. You want to maximize your sampling rate and bandwidth, so sampling rate should be 5 to 10 times the oscilloscope bandwidth. This is mainly because the oscilloscope frequency response will be less sharp in its roll-off characteristic if you oversample fast. If you don't oversample, then you're going to run into distortions caused by a very sharp cutoff in the oscilloscope. The oscilloscope rise time in general should probably be 10 times the rise time of what you're measuring. This is sort of a rule of thumb in terms of getting the best accuracy on a measurement. And using waveform averaging in whenever possible. But again, high resolution waveform averaging are best applied to waveforms when they're in the on state or off state rather than in the transition states where you need to have high sample rate, and resolution is less important. Measuring current is an important aspect of any power supply, and there's a couple of different ways to do it. Kind of a traditional way to measure current is using a current probe. These are usually clamp-on devices that measure both AC and DC current with a Hall effect device that allows you to do that. One of the things about this type of current probe is they do need to be demagnetized because they will retain some magnetism after a measurement, and you need to basically zero it out to get an accurate DC current measurement. The biggest, I think, limitation of these kinds of probes is they require some sort of a loop in the circuit to measure it. So you need to have a wire loop to clamp this thing around, and since these probes tend to be fairly large relative to a lot of power supply circuits, it's often difficult to find a loop like this, or to build it into your circuit it disturbs the actual design by adding an inductance. So not always easy to use this kind of probe. And they do have limited bandwidth. Most of them typically are about 100 megahertz or so of bandwidth, so if you're looking for high frequency current information, this may not be the best choice. What more and more is being used nowadays is a shunt resistor method, and this idea is very simple. You basically put a series resistor in your circuit and then measure the drop across that resistor. Now, in order to not disturb the circuit very much, you want a very low resistance value, so typically 1/10 of an ohm or so is used for this purpose. One of the key things about this resistor, though, is it needs to have a very stable value versus both temperature and current. So in cases where you're driving higher currents through these resistors, it may be difficult to make them maintain their original resistance value. So a lot of these are specialized parts that are designed to be very stable. The benefit of this method is it has extremely high bandwidth, and so you can see measuring with, for example, a high bandwidth 500 megahertz or gigahertz probe, you could actually measure current variations at those rates. So it gives you a lot more detail in the current waveform. One other limitation of this that I should mention is that the voltage drop clearly across a small resistor like that can be extremely small. So it might be very difficult to measure the current because it represents a very small voltage, which is maybe hard to measure on the oscilloscope. So you need an oscilloscope with very low noise or a probe with lots of gain in it. An interesting method for doing this that at least gives you a partial measurement is to use something called a near-field probe to probe the near field around the inductor. And the nice thing about this method is it doesn't disturb the circuit. No special probing points or resistors need to be added. You just simply use this current probe as is shown in the lower image and kind of touch it right to the circuit. Limitations of this, of course, is that it only measures AC current. It won't measure the DC value because we're looking at basically a radiated magnetic field to pick up with this probe. And it has somewhat limited sensitivity because, again, the gain of the probe might not result in a big enough voltage to measure clearly. But the benefit of this, and I think the strongest benefit, is beyond not disturbing the circuit, is that it can measure very small geometries, which are pretty common in switch mode supplies these days. So you can actually measure a circuit that is small enough that you can't even get a probe near it, but the near field probe can touch down right on that. A little bit of detail on the near field probe. It works by capturing the magnetic field, or H field, that's emitted by a wire carrying a current. So if you can imagine the wire leading to the inductor or the inductor itself, as the current's flowing through that, it's going to generate a magnetic field around it, and the near field probe simply picks up this magnetic field, or H field. Typically, a near field probe is a loop, like shown in the schematic on the right, but in a lot of cases, you have very small geometry near field probes, one of which is shown on the left. This is a very small, almost like a point that you can touch right onto the traces or IC legs and measure the current that way. And basically, in order to measure the current equivalent that's captured by the the near field probe, you take the voltage as measured in the near field probe, and you simply integrate it to get the current. The nice thing about the integration is that function is usually available on most oscilloscopes, and the active integration actually reduces the noise in the measurement. So the small signal you measure with the current probe is actually enhanced by the integration process, and you get a pretty decent measurement out of it as well. Just a quick word on probe de-skew. Normally when you're measuring input and output waveforms, de-skewing is not a big issue because things are operating at a slow enough rate and you're not looking at the transitions very closely, and so the measurements don't sort of depend upon things lining up. But if you're measuring things like switching loss, where you're actually measuring the current and voltage going through the switching transistor, then de-skewing becomes very important. And the three waveforms here show the effect of having either skewing where the current waveform is early or late, the first two images, or right on top of each other. Depending upon the skew, you can either under or overestimate the loss in a switch. So getting these things aligned perfectly gives you the most accurate measurement of the switching loss. Although I don't think switching loss is a common measurement that folks do with switch mode power supplies, unless they're designing them, and use models not so much. And here's an example of how the de-skewing process works. You basically attach the current and voltage probes, and we show that in these images on the top right, and then you measure the current and voltage waveforms on the oscilloscope and simply adjust the skew. In a lot of cases, there's actually an automatic de-skew in the oscilloscope, which allows you to automatically line those waveforms up. You don't even have to do it by hand. So I want to go into a quick overview of a measurement example. So we're going to look at a simple buck converter, and this is a schematic view of what we're going to be looking at. This has actually got two FET switches and a controller circuit that are all integrated onto one chip. This is a small chip. It's about 3 or 4 millimeters on a side, so it's something really tiny and not easy to probe. So the probing points we're going to use are the input voltage, the switch node voltage, which is available because the inductor is external from the chip, and then we're going to look at the output current and voltage as well. First thing you typically want to do is look at the startup behavior. So you're interested in seeing how the power supply goes from the off state to the on state. Now there's a couple of different ways to do this. One is called kind of a cold start behavior, where there's no voltage applied to the regulator, and then you apply voltage, and then you see how long it takes to get to regulation. Another measurement is a so-called soft start or warm start, where there's actually voltage applied to the regulator, but then you turn on the regulator afterwards. We're going to look at a soft start in the next slide here. So there's 3 waveforms here, and it's basically soft start waveforms for 3 different loading conditions on this particular power supply. On the top left, we have the input and output voltages for no load condition. So there's no load applied to the power supply. And then on the top, on the middle and the bottom is for a 20 ohm load applied to the output of the supply. And then on the far right is for a 5 ohm load applied to the output of this power supply. The 2 voltage waveforms, the pink one on the top is the input voltage, and the blue one on the bottom is the output voltage applied to the load. Now, as mentioned, this is a warm start, so the input voltage is already at 5 volts, as you can see. And what we can see here on the waveform is 2 things. There's what looks like sort of a fuzzy cloudiness around the central waveform level. This appears in both the input and output waveforms, and that's actually ripple from the switching node operating. So what you're seeing there are little spikes on the waveform that result in ripple that can be observed in the input and output. Now notice with the no load condition, there's a lot of ripple during the startup process on both waveforms, but when it gets to final regulation, which in this case is at 1.8 volts, you see that it's pretty stable and clean, and this makes sense because it's really not driving anything, and so the switching is very clean and quiet. The time it takes to go from the off state to the on state, in this case, is about 3 milliseconds. This is an important aspect because one always needs to know how long it takes to get to final regulation. So we can clearly measure that. Now, one of the benefits of using an oscilloscope with a high sample rate and deep memory is that you can both measure the ripple voltages that are very, very fast and very high frequency, along with the long-term trend of the voltage, which can take milliseconds. And so having both high sample rate and deep memory allows you to see this. If you had to trade off, for example, sampling rate for memory depth, those ripples may not be visible in the waveform, but of course you would see the overall trend. So noticing though with the 20 ohm load that we get a little bit of ripple now in the output signal at regulation. This is because now we're driving a load, so there's more current going through the inductor and also through the capacitor in the output, and so we're seeing more ripples. Now on the 5 ohm load, things get pretty bad here. We'll notice that the ripple voltage is quite high. At least it doesn't seem to get any better when the regulator gets to regulation. And this is a hint of a symptom here. So we've got a system that's turning on apparently well, but there's a lot of ripple even at full regulation. This is something we want to investigate a little bit closer. So the next thing we want to look at is to examine that output voltage ripple and the spectrum of that. So the two things we want to look at here are the peak-to-peak ripple voltage as well as the spectral content in that ripple. And so in order to do that, we simply probe at the output of the power supply, right as it goes into the load, both the voltage and current if you can. In this case, we're just going to look at the voltage waveform. So here's a measurement of the output ripple, and again, we're using a passive probe with a long ground lead. And in this case, we're actually seeing a fairly high ripple voltage, I think. This is actually turning out to be, and it's a little hard to see on there, I think it's about 150 millivolts of ripple voltage on this thing. And so this is the with the long ground lead. And if we switch to the short ground lead, and next slide here, we can see that reduces the ripple voltage considerably. And now we're looking at, I think, about a 26 millivolt ripple voltage on this guy. The previous one was about 80 millivolts of ripple. So by shortening again the ground lead, we're able to see less of the ripple voltage. And again, it just points to the need for making sure your ground leads are not too long. This next slide here is actually showing the same ripple voltage, but now measured with an active probe. And in this case, the ripple voltage is a little bit bigger. And the reason for that is there's more high-frequency content visible in this waveform. You're actually starting to see a little bit of the variation of the inductor current leaking through to the output voltage. And that's why you see those sort of sharp edges in that waveform. And again, the high bandwidth active probe allows you to see that detail a little bit better and actually gives you more information about what the actual ripple looks like. And again, this is important if your circuit is sensitive to the high frequencies, and normally the downstream circuitry may not be real sensitive to the ripple. However, you might end up with EMI problems if this becomes too big. So looking at the next slide, we're going to start looking at the output voltage spectrum. And so normally what one would do is they would take the ripple voltage and do an FFT on the oscilloscope, which gives you the frequency domain information. And here we're showing the spectrum with both the 5 ohm and 20 ohm loads. And so you can see the spectrum shows lines that exist at the switching frequency and at harmonics of the switching frequency. If you look real closely, they don't look very different. In fact, they're pretty much the same. And the frequency range of this measurement is from DC to about 30 megahertz, sort of a traditional way of looking at ripple voltage. And what you want to see is the ripple voltage falling off versus frequency, which it seems to be doing in both cases. But as we observed, the peak-to-peak voltage is actually bigger when we have the 5 ohm loads, so something's wrong here somewhere. If we expand out the frequency range, so now we're looking from out to about 500 megahertz on the spectrum, then we can sort of see the evidence of what's going on. On the bottom left corner is the ripple voltage with the 5 ohm load. And notice the spectrum has a lot of broadband energy, and that energy is actually at fairly high frequencies. The energy is somewhere between 100 megahertz and 300 megahertz. We've got a lot of RF energy basically being transmitted to the load. And this is a problem because it does generate ripple, but worse yet, it can be a very big EMI problem because that could couple into external parts of the circuit, which could radiate that out, and you could end up with lots of interference. So that's the 5 ohm load, and that's really where the problem is. So we didn't see in the spectrum well, we didn't look out far enough. So having high bandwidth allows us to see the RF part, which can be a problem moving forward. Notice with the 20 ohm load, things are much better behaved in terms of the spectrum, and of course the peak-to-peak ripple was smaller as well. So the next thing we might want to look at is the transient response. Now, transient response of the output is a little different than looking at ripple. What we're looking at here is the response of the power supply to an abrupt change in load condition. This is pretty common because a lot of circuits aren't constant, but rather they switch off and on, and so we want to see the response of that. Now, transient response is a pretty big topic. We're just going to look at it basically here, but a lot of the transient response can lead to things like stability in power supplies, which can be a real problem. Now, the quick way to do a transient response measurement is to add a current step to the output. So you want to just abruptly change the load. A couple of different ways to do this. One way is to use an electronic load where you can actually switch in different loading conditions. Another way to do this is sort of inject a current pulse, and there's ways to do that as well. And then you can actually take your active circuit as designed and just inject extra current and see what the power supply does. In this case, we have a power supply where we're switching in various different loads, and we're watching the output voltage. This is a pretty long time sweep here on this picture, and you see there's a waveform with no load, with a 20 ohm load, and then with a 5 ohm load, and finally with a 4 ohm load. A couple things you can notice on this picture. One is the voltage appears to drop for each loading condition, and this makes sense from the standpoint that with the lower load we're driving more current, but if the power supply was working properly, we shouldn't see this dropping voltage. So it's obviously pointing to a problem that we have with the supply. In the no load condition, I'd expect the regulation to be a little high because we don't really have a nice feedback there. But in the 20 ohm, we're right at about 1.8 volts where we need to be. And you see the ripple around it is fairly small. But then as we go to the 5 and 4 ohm loads, the ripple becomes quite large and the actual average voltage is dropping off. So again, a hint of a problem. What we look at in the transient behavior is the overall shape of the central dark yellow portion of the waveform. And so what we can do is we can filter out some of that ripple and just look at the filtered waveform. And here we're just zooming in on the one transition. And what we're looking at is how much overshoot in voltage there is. We want that to not be very big, but we also want to make sure there's not any ringing beyond that first spike. So any ringing or undershoot could be the indication of a potential stability problem. And so we look at this to analyze that. And right now, this particular supply doesn't seem to have that problem, although it does have a lot of ripple with the 5 ohm load. The next thing we want to look at to try to figure out where this problem is coming from is we're going to go back to the switch node and look at the switch node voltage and the inductor current. So now we're going to go inside the middle of the supply, right at that node between the two transistors, and we want to measure the voltage there, and we also want to measure the current. So to do this, we're going to use some averaging, and we're going to use some high-res mode. We're actually combining the two in this measurement. And the reason we're doing that is because we care, in this particular case, more about what the voltage and current look like during the period which the inductor is charging and discharging. And at those points, the waveform is fairly flat. And you can see here, it's a little bit hard to see, but I'll point it out, that there is a slight slope on the voltage waveform, which is shown in background on blue. And this slope is caused by resistance in the switch as well as any additional resistance, let's say, in the inductor or external circuits. And you can see the slope is fairly shallow, and it's reasonably good. And also, if you look at the inductor waveform, which again, here we measured using the near-field probe with the integration, you can see it looks fairly linear, although not perfectly linear, so that might hint at a problem that we have here. If we increase the load to 5 ohms, and we get this measurement, a couple of things that have changed. Now, it may not be real obvious, but the slope of the voltage waveform at the node is actually steeper now, and that indicates an increase in resistance. So either the transistors have increased resistance, or more likely the inductor is starting to exhibit some additional resistance beyond what you'd expect. Also notice that the inductor waveform, again measured with the near-field probe, is curved. And the curvature of that indicates that the inductor is no longer operating in its ideal mode. It's in fact becoming saturated. And so what happens here is that waveform becomes curved because in saturation, an inductor starts to look like a very small resistor. So what we're getting is additional resistance and the inductor no longer operating as it should. And this is really the root cause of our problem. The reason we have all that high ripple voltage is that this inductor is undersized and it's not operating and filtering properly. So what we did with these measurements is we noticed that increasing the load to 5 ohms resulted in a reduced voltage, lower by about 200 millivolts from what it should be at regulation, as well as increased ripple and increased spectral power above 100 megahertz. By looking at the switch node, we noticed that the inductor current became nonlinear with the 5 ohm load. And in addition, we noticed that the switch node voltage slope increased, as well as the rise time got faster. And both of these are indicative of that overload, or that saturation. The problem was trace the undersized inductor, which we then go out and kind of fix, get a new one. So that's kind of a quick overview of some measurements with a reasonable example. Hopefully that is helpful, and I'll pass it off to Chris right now.
All right, thanks, Mike. Great presentation. Before we begin today's Q&A, please fill out the feedback form that's opened up on your computer. To complete the form, please press the Submit Answer button at the bottom of the page. Thank you in advance for filling out the feedback form. Your participation in this survey allows us to better serve you. And now we'll move on to the question and answer portion of the event. As a reminder, to participate in our Q&A session, just type your question into the text box located below the media player and then click the Submit button. And with that, we're going to get started with some questions already received during the webcast. So our first question is going to be, Mike, what is the reason for using or designing switched mode power supplies rather than DC supplies?
So I think the primary reason for that is efficiency. So ideally, if the switches were perfect, switch mode power supplies would have 100% efficiency with no loss or heat generated. DC supplies or linear supplies have a lot of loss because what they do is they typically scrub off the extra voltage as heat, and so they're terribly inefficient. So really it's the efficiency. If you think about small handheld devices and battery life, that's what sort of drives a lot of this.
All right, and our next question for you, won't the near field probe affect slightly the permeability profile of the inductor?
Yeah, actually, good point. Yes, in fact, there's no free lunch here. Yes, if you put the near-field probe next to the inductor, it will have an effect. However, the near-field probe is pretty open in design. It's got a fairly low self-inductance, so it's not going to have a very big effect. In fact, a fairly minor effect on that. But that is a good point. It will have an effect.
And another question for you here is, isn't it better to have more bits on the scope to start with rather than, say, averaging?
Yeah, so that's actually a good question, and it's really kind of hard to answer it in a direct way. The problem is when you look at the number of bits on the oscilloscope, that is the way the ADC is designed at DC. So for a DC voltage, it will have that number of steps. But when you put a complex AC waveform in, lots of things come into play, nonlinearities, distortions, and noise from the ADC, so that the so-called effective bits are actually much less than the bits of the ADC itself. And so really what you're looking for in measuring power supplies is not so much the actual bits of the ADC, but the effective bits, but more importantly, how the ADC works in averaging. Because as you average more waveforms, ideally the noise would decrease with the square root of the averages. At some point, that averaging gain goes away, and really what you want is the ADC who allows the largest amount of averaging gain, because that's where you really get the precision. And again, it's not obvious from looking at the number of bits where that point is. It's more of a test that you need to do.
Another attendee has asked, can you make calibrated current measurements using the near-field probe?
Yeah, so that's actually something that can happen. One of the things that you could do is sort of run a known current through a wire, and simply use the near-field probe to measure that. And with a known current, you can actually build a calibration factor at different frequencies. So that's a possibility, yes. But again, it's important to keep in mind that you cannot do DC, so it's only AC.
Very good. Another question for you here. What are typical switching frequencies in switching PS?
Covers a large range of values. Some of the larger high current supplies switch in the kilohertz range, where a lot of the smaller high efficiency supplies will run in 1 megahertz or even faster. the trend is towards faster switching frequencies. The benefit of the faster switching frequency is really ultimately efficiency.
All right, and another one for you here. Any suggestions for near-field probes? We were using a Tech DPO 7254C shunt resistors have shown to have too much noise.
Oh, you got to get rid of that tech scope. No, just kidding. No, so so the near-field probe might help you out. I've seen these things with the shunt resistors. So one of the things you might need to do is get a little preamp, and some of these near-field probes actually do have preamps available with them. And really make sure that you can get as much gain as possible out of the scope. And I would try just as many different models as you can. One of the things about scopes is the more high bandwidth and expensive ones tend to have better sensitivity, so you might want to go to maybe a higher end scope for that. But the other benefit is the integration function will average out noise, so it's going to give you a little more sensitivity, and certainly worth a try to see if you can get what you want. But again, bear in mind that the shunt resistor measures DC, whereas the near field probe is only going to do AC. So as long as you're okay with that, the near field probe will do the job for you, I think.
All right, and here's one just more of a statement, but asking if you could maybe talk a little bit about zero current switching.
That's a good one. Yeah, I don't think I can get into that right now. Sorry.
That's all right. We'll give you
give me a pass on that one.
Yeah, we'll give you a pass, and you'll be able to get back to them post-show. Another one for you here. What do you recommend for the active probe with greater than 70 megahertz and greater than 2 kV?
Yeah, so the kV is a tricky one because there's not a lot of good active probes that'll supply that sort of bandwidth and that voltage. I think there are a number of probes in the 1400 volt range that'll give you about 100 megahertz, but yeah, 70 is a little tricky. The biggest problem with anything like that, any kind of a high voltage probe, is that safety requirements sort of require that you use large insulated wires to attach to your circuit. And as soon as you start using these large wires with these big hooks on them, the actual probe tip destroys your bandwidth. So unfortunately, not a lot of good ways to measure that kind of thing at a high bandwidth, although I know it's something that people want to do.
All right, Mike, and here's another one for you. Aren't higher switching frequencies associated with higher EMI?
EMI is a tricky subject, so there's not always a one-to-one correspondence, but yeah, theoretically a higher switching frequency could potentially lead to EMI. But the whole problem with EMI, or the issues with that, are usually you need a coupling mechanism and you need some sort of a radiating element, an antenna of some sort in your circuit for actually to have an EMI. So the presence of high frequencies by itself won't result in EMI, but what will is poor grounding that leads to maybe coupling of that high frequency to the outside world. So make sure you ground things carefully, and then you won't have a problem. The nice thing about high switching frequencies is the efficiencies they give you.
And it looks like we have one more question for you. Should SMPS be shielded when driving very sensitive amplification circuitry?
Yeah, so definitely if the switching frequency is going to start getting into the frequency range of your amplifier. But I guess most importantly is I can't emphasize grounding enough. I mean, it's really important to be careful about how one grounds around the switching, to make sure there's good return lines with low resistance. That, more than anything, is going to prevent these problems from happening. And shielding may be a last resort, but I think if you really ground things well, you may not have to worry about the shielding.
All right, Mike. Well, that looks like all the questions that we have for today. Do you have any quick final thoughts before we wrap up?
No, like as always, I'm just really happy everybody was able to join us. I'm always, honored to be able to speak to you all out there. So I hope it was helpful and at least a little bit interesting, and I look forward to doing one of these in the future.
All right, Mike, great job. Within the next 24 to 48 hours, you're going to receive a personalized follow-up email with details and a link to today's presentation on demand. And additionally, you'll be able to view today's event on demand by visiting www.techonline.com. Thank you for joining us for today's webinar, Troubleshooting Switched Mode Power Supplies, brought to you by Rohde Schwarz, Tech Online, and broadcast by UBM. This webinar is copyright 2014 by UBM. The presentation materials are owned by or copyright by, if that is the case, by Rohde Schwarz, Tech Online, and UBM, who are solely responsible for their content. The individual speakers are solely responsible. The individual speaker is solely responsible for his content and opinions. On behalf of our guest, Mike Schnecker, and Rohde Schwarz, I'm Chris Keach. We'd like to thank you for joining us, and we hope you have a great day.